So these are our team members. We have Irfan Akmal, Idlan, Muaz, Zurai Fikri, Ashnam, and me, Fatin Alia. Traffic management is the organization, arrangement, and guidance and control of both stationary and moving traffic, including pedestrian and bicyclists and other types of vehicles. It is important to study each of the elements to provide a safe, orderly, and efficient movement of persons and goods, and to protect and at the same time enhance the quality of the local environment on and adjacent to traffic facilities. It is obvious that the number of vehicles are increasing day by day, and this led to traffic congestion, especially during peak hours in urban and suburban areas. In Johor, most of the intersections are signalized intersections, but some of them still facing few issues such as excessive delay for motorists and increased accident frequency due to improper design of road junction. Hence, this eventually affects the sustainability of state's transportation system. As a traffic engineer, our team are required to conduct a traffic assessment at Signals Junction. We have chosen a T junction at Jalan Pontian Lama Skudai, Johor as our study location. The chosen T junction includes 6 different interactions to study. The objective is to check the existing phase and timing of the traffic to determine the level of service (LOS) and to propose new signal timing design for the junction and choose the best alternative for the signal timing design. Upon completing the study, we realized that it is important to know traffic design because we can identify the traffic level of service through calculation and theoretical analysis. Then, we can recommend relevant approaches to improve the traffic of our study location at Jalan Pontian Lama Skudai, Johor. As a team of future engineers, this study is very important and useful for us to learn how to propose and construct different solutions for roadway signal timing design. As for the outcome of our study, we aim to provide the road users as a safe and efficient road traffic system through our proposed solutions.
First, we will do a topic study and distribution works. Secondly, we will pick a site and survey the site if it's suitable. Then, the data will be collected at site that has been picked. Next, the collected data will be calculated and then we will design the alternative based on calculation that we obtain. If it's okay, we will choose the best system with completed cycle time setting. If it's not okay, we will redesign new alternative with suitable total saturation flow. Lastly, we will conclude at the end along with relevant data collections.
In order to analyze the selected site, some data are needed to be collected for the existing geometric design. For instance, the number of lanes from each direction are important together with the width of the lanes. The cycle time for each signal indication of a lane is needed to identify the period needed to complete the sequences of 3 phases at the T-junction. The traffic signal system is determined by recording the complete cycle time of the traffic for 3 times and every cycle time was calculated. The sign of each lane is recorded to determine the service given for the road to the traffic users. Besides, the most important data needed to analyze the signalized system at the chosen site is the traffic volume from every direction at different phase for an hour. Hence, we choose to do it during the peak hour of the weekday period, which is around 9 a.m. because most of the people are still on their way to work. Data such as turning radius and gradient of the road could be roughly assumed. The main reason we choose this T-junction as our site to study is because it has a back traffic delay problem. We observe that the condition is even more severe during the peak hours. Hence, we need to create a few alternatives that redesign the fixed time signal system and choose the best value that is the lowest. The objective in geometric design are to optimize efficiency and safety while maintaining cost and environmental damage. Due to the restriction that we had, Google Street View will be used to analyze the road width distance. After that, we will use traffic volume count as part of transportation surveys. In our group will be recording number of vehicles passing on a predetermined location by using vehicle tally sheet. Traffic volume is the number of vehicles passing through a road over a period of time, and it is usually expressed in terms of passenger car unit or PCU. The data we have collected will then be organized according to the types of vehicle so that we can draw inferences on the basis of data collected and provide possible solutions and improvement suggestion for the problem identified. This is the analysis method that we obtained from traffic engineering notes from Cheros Ismail and also JKR Arahan Teknik Jalan 1187 from 1987.
Assalamualaikum and hi, I'm Ashlam Razali and I will present about the data analysis. For the current traffic, it was designed as three-phase system. For phase 1 is combination movement of south and east, phase 2 is combination movement of west, east and south, and phase 3 is combination movement of west, east and south. Then we check the total volume in a straight right turning phase. In phase 1, there is conflict between south to east and east to west, which will get 24,857 less than 50,000 volume, then it is adequate. But for the turning volume is 371, which greater than 100 and it is not adequate. Same goes to phase 2. The conflict is between east to south and east to west, which we get 10,586 less than 50,000 and it is also accepted. But for the turning volume is 158, which is greater than 100 and is not adequate. For phase 3, there is no conflict. From the calculation in the table, the maximum saturation flow we get for phase 1 is 0.54, for phase 2 is 0.17 and lastly for phase 3 is 0.17. Then we sum up all the values and we get 0.88, which is greater than 0.85. Then the value is not accepted. Since the saturation flow is too high, we need to redesign the traffic flow by come up with a few alternatives. For the first alternative, which is alternative A, we assume there are three phases at the traffic. For the phase 1 is all movement from south, phase 2 is all movement from west, and the phase 3 is all movement from east. Then, from the calculation in the table, the maximum saturation flow is 0.54 for phase 1, 0.12 for phase 2, and lastly for phase 3 is 0.13. And then we sum up all the values, we get 0.79, which is less than 0.85, and the values is accepted. So the traffic flow here is accepted.
And now we're going to look at the alternative B. For alternative B, we design it to have three phases. For phase 1, we have all movement from south, and for phase 2, we have all movement from west to east and east to south. And for phase 3, we have all movement from west and south to west. And now we're going to look at the table we use to calculate the Y maximum value. As you can see in the table, we take the Q of low value in vehicle per hour from the data we obtain at the targeted area. And then after all the calculation, we obtain the maximum Y for phase 1 is 0.54, for phase 2 we obtain 0.16, and for phase 3 we obtain 0.17. After that, we do summation of all the maximum Y value, 0.54 plus 0.16 plus 0.17, and then we obtain 0.87, which exceeds the 0.85 limits, and this is not adequate to be implemented in the targeted area. And now we are going to look at the last alternative that we propose, which is alternative C. For alternative C, we will design it to have three phases. For the first phase, we have all movement from south and east to south, and for the phase 2, we have all movement from west, and for phase 3, we have all movement from east and west to east. And now we're going to look at the table we use to calculate the maximum Y value. Same goes to the previous alternative. we take the Q or flow value in vehicle per hour from the data we collected at the site. And then, after all the calculation, we obtain the maximum Y value for each phase. For phase 1 is 0.54, for phase 2 is 0.12, and for phase 3 is 0.13. After that, we do summation for all the maximum Y value, 0.54 plus 0.12 plus 0.13, and we obtain 0.79. And is not exceed the 0.85 limit, and this is adequate to be implemented in the targeted area.
Okay, now I will be talking about the optimum cycle calculation. So for the optimum cycle calculation, we have made some assumptions, which are the all red period equals to 2 seconds, amber 3 seconds, and lost time due to late start 2 seconds. So we calculate the intergreen period by using the formula of I equals to R plus A, and we got 5 seconds. And then the total lost time per cycle, we got 12 seconds. And lastly, we calculate the optimum cycle time by using the formula of 1.5 L plus 5 over 1 minus 5, 1 minus Y. And we got 110 seconds. So by calculating the minimum and maximum of CO, which the minimum 0.75 CO, and we got 83 seconds, and 1.5 CO, we got 165 seconds. Our group agreed to take the value of optimum cycle of 125 seconds. So next, we calculate the effective green period GN with the formula of GN equals to the Y max times our optimum cycle time minus 12, which are the total lost time per cycle, over our 0.79, which our total maximum saturation flow, which 0.79. And we got the answer of G1, G2, G3, which are 77, 17, and 19 seconds respectively. And then we calculate the actual green period by using the formula of Gn equals to G capital N equals to Gn plus 2, which are the lost time due to late start, plus 2 all red period. And we got the answer of G capital 1 equals to 81 seconds, G capital 2 21 seconds, and G capital 3 23 seconds. And lastly, we calculate the controller setting Kn by using the formula of Kn equals to G capital N minus 3, which are our amber time, and minus 2 all red period. And we got the answer of K1 equals to 76 seconds, K2 16 seconds, and K3 18 seconds. And lastly, below we attach our alternative C traffic timing diagram. Okay, now we have calculated the level of service for alternative C, and this is what we got. So first, we have calculated for all the movement on phase 1, phase 2, and phase 3. So on the phase 1 movement, south to west, south to east, and east to south, we got all the three movements level of service B. While the phase 2 movement west to east and west to south, and also phase 3 east to south, east to west, and west to east, we got all the five movement on phase 2 and phase 3 level of service E. Thank you.
In conclusion, as this three-arm signalized intersection at Jalan Pontian Lama has two lane on all approach, we choose a three-phase system, which is the most suitable system for this type of junction. As we compare the current traffic timing, the value is slightly higher, 0.88 greater than 0.85, where we'll need other alternative for the traffic junction. The most suitable alternative is alternative C compared to the other two alternative A and B. The traffic timing calculated is 0.79 less than 0.85. The width of the lane we use is 3.5 meter, same for all lane from all direction. As we calculated, the alternative C traffic timing diagram is C naught equal to 125 seconds, which is much better and lesser time than the current traffic timing diagram C naught equal to 148 seconds.